Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 28, practice 10, in which we will solve the last and the final problem of this course, the problem number 29, in which we are given two distinct fixed and coplanar circles, the lengths of whose radii are distinct and none of which is located strictly inside of the other, which means that in the problem number 29, the only legal juxtapositions of the input objects are the following. The two input circles are located strictly one outside of the other and are not in contact. The two input circles touch each other externally at a certain point, and the two input circles intersect over two distinct points. And under these conditions, we are asked to find a way to reflect the given input circles into a pair of circles, the lengths of whose radii are exactly the same. In other words, in plain English, in the problem number 29, we're asked to find a way to reflect a pair of differently sized circles into a pair of equally sized circles. We will be solving the problem number 29 using the combination of the reverse order and the transform and conquer problem solving approach, as was explained in the previous episodes, following the mandate of Terry Tao of learning and relearning the material in the current field of mathematics, so as to put the mechanics of manipulation of the underlying notions into our bone marrow and thus free our brain cycles for other creative work. As such, in this problem, we assume that we somehow obtained a pair of equally sized circles already. How this pair of equally sized circles that is sought after was generated, produced, we do not know yet, and we do not care at the moment. And that means that we have a pair of equally sized circles which are not in contact and are located one outside of the other, shown on the left. The pair of equally sized circles touch each other externally, as it is shown in the middle, and the pair of equally sized circles that intersect over two distinct points. And now that we made this brave assumption, we ask the following question as the reverse order problem solving approach suggests we do. What chain of tactically advantageous if P then Q implications that originates at the problem's artificially solved state and terminates at the problem's not solved state can help us unlock a traditional or sought after forward flow of causality solution? A key observation that unlocks an elegant solution of this problem and that you are expected to make on your own is the following. Let us agree for the sake of definitiveness that the input circles in our problem are named S1 and S2, and under a mystery inversion of the real plane with respect to a certain circle, the images of the circles will be S'1 and S'2. Then, again, reasoning in reverse order, assuming that the sought after equally sized circles have been somehow produced, regardless of their legal mutual juxtaposition shown here, here, and here, every such pair of circles will be symmetrical with respect to a straight line shown in red and named L prime that is constructed as follows. Let's say O'1 is the center of the reflected circle S'1, O'2 is the center of the reflected circle S'2. These 2 points are distinct. They define a unique straight line that passes through them. They define the unique line segment that is delineated by the points O'1 and O'2, and consequently such a line segment, regardless again of the mutual legal juxtaposition of the output circles or reflected circles, this one and this one and this one, this one, will define a perpendicular bisector that cuts the corresponding line segment O'1, O'2 into two equal halves by length, and that is perpendicular to that line segment. In all cases, such a construct is possible. And here it should be understood that the symmetry of the two reflected circles S'1 and S'2 is with respect to the straight line. There is nothing fancy going on here. No reflection in the circle, no reflection in the ellipse, no reflection in the hyperbola, no reflection in the parabola. Good old middle school so-called straight line symmetry, and in all these cases the images of the circles are produced as follows. Pick any point on any one circle. For example, let's pick the point on the circle S'2 over here. Then through the chosen point we construct a straight line that is perpendicular to the axis of symmetry, or the straight line of symmetry, L prime. That straight line will run as follows, like so, and then it must be perpendicular to L prime, and then from the point of intersection of this perpendicular with the line of symmetry, we measure the same distance in the opposite direction. That is equal to the distance from this point to our original point on the chosen object. We measure this distance here, we obtain the point, which is the image of the point P in the straight line, and then we do so for all the points, and that is how we reconstruct the image of a given object in the straight line L prime. And the question now is, if this is an Eulerian observation, which on one hand is very straightforward, it is a seemingly childish observation, but on the other hand, this key observation already unlocks an elegant solution of the problem number 29, and the question is, how? The next observation, or the next implication that you were expected to make on your own, is the following. In the last two episodes, I already mentioned it twice, that through the set of theorems that we proved in this course, we actually showed that topologically straight lines and circles are equivalent in the following sense. Any straight line that does not pass through the center of inversion is taken into a circle that does pass through the center of inversion, and conversely, any circle that does pass through the center of inversion is taken into a straight line that does not pass through the center of inversion. And in our case, if we made our first implication in the previous segment, which amounts to the following: if a pair of equally sized circles is a solution of our problem, then in any of which legal juxtapositions these two equally sized circles will be symmetrical with respect to each other in a straight line L prime, which is the unique perpendicular bisector that is defined by the two distinct centers, O'1 and O'2, of the sought after equally sized reflected circles S'1 and S'2. But now that we know about this topological equivalence between straight lines and circles, the next implication that we make over here is the following. In its previous life, the straight line L prime used to be a circle that passed through the center of inversion, let's say some point P, if we know what that center is, or if we do not know what that center of inversion is, through a center of inversion. Wonderful, but how does that help? Well, with another clever implication, the previous observation actually solves the problem number 29 completely, and we can show it as follows. Let us agree that the input circle S1 that is shown in yellow over here and the input circle S2 shown in yellow over here are positioned one outside of the other. Let's say these input circles do not have any points in common, and just for definitiveness, let's say that the radius of the circle S2 is strictly larger. This is the radius R2 of the circle S2, R1 is the radius of the circle R1, and let us say, again, for definitiveness, that R2 is strictly larger than 1 for R1, for example. Then in this problem, we seek a mystery for now inversion of the parent plane symbolized with the letter uppercase I with positive power in the center P, which is not known for now, and the radius R, also not known for now, such that the circle S1 is taken into the circle S prime 1. The circle S1 is taken into the circle S prime 1, shown in red over here. And under the same inversion, the circle S2 is taken into the circle S prime 2. The circle S2 is taken into the circle S prime 2, also shown in red over here, such that the radii of the reflected circles the radii are exactly the same. So here I show the mystery circle of inversion lowercase c with the center at the point P and some radius for, and right now we will realize what the center of inversion should be and what the radius of inversion should be. We also constructed a very short chain of implications saying that if the pair of circles S prime 1 and S prime 2 that is sought after has exactly the same size, the lengths of the radii of the circles are the same, then there must exist a unique straight line L prime with respect to which these two circles must be symmetrical. And we also made another observation that in the previous life, through the magic of topological equivalence, the straight line L prime, shown in red over here, this straight line, used to be a circle that did pass through the center of inversion. Right now, we designated the center of inversion with the uppercase P, the point shown over here. The circle L is shown in green over here, and its center is shown over here, the point O. Now, the properties of the green circle L are quite interesting and quite helpful. And what are they? Well, first of all, under the same mystery for now inversion of the parent plane with the positive power centered at the point P with some radius R, that circle must be taken into the straight line L prime. This is our demand. Remember, through the magic of the topological equivalence of straight lines and circles. And the first property of the circle L is the following. The center of the mystery inversion sought after is located precisely on the circle L somewhere. We do not really care where it is, but it must be located on the circle L. That is why we can refer to it as a circle of inversion. Any point P taken on the circle L will do for us. And now we realize that any strictly positive real number R will make it good enough for the radius of inversion. And that is how we define our circle of inversion C centered at the point P with the radius R. Now we make the following clever implication, which in a way is staring us in the face. All we have to do is reveal it. So the implication here is the following. If the image circles S prime 1 and S prime 2 are symmetrical in the straight line L prime, the image circles S prime 1 and S prime 2 are symmetrical with respect to the straight line L, then the pre-images of the circles S prime 1 and S prime 2, or the original circles S1 and S2, must be what? We demand that they must be symmetrical in the pre-image of the image straight line L prime. But what is the image of the what is the pre-image of the straight line L prime? Well, by our demand again, the pre-image of the straight line L prime is precisely the green circle L, which houses a center of inversion. Make sure that you comprehend this implication, this idea that you were expected to generate on your own, and in some sense it's not really that difficult if we detach ourselves from all the details and symbolization and think about it at the very basic or raw level without any specific pedantries, technical pedantries, in some way intuitively. The images are symmetrical in something, That means that their pre-images must be symmetrical in the pre-image of that something. That is the basic, very straightforward, simple, in some sense, implication. But once we make this implication, the solution of the problem becomes evident. The other property of the circle L that is of interest to us is the following. Not only that circle houses a center of inversion P, but that circle plays the role of the circle of inversion with respect to which the circle S1 will be taken into the circle S2, and the circle S2 will be taken back into the circle S1. In other words, in our implication, we claim that if the image circles S'1 and S'2 are symmetrical with respect to each other in the image straight line L', then the pre-images of the circles, the circle S1 and S2, must be symmetrical in the pre-image of the straight line L', or the circle L. We can also here designate, let's say, this whole thing is L, inversion of the parent plane with the positive power in another point, in another center, O, not mix the point P with the point O over here. And the radius R large. These two magnitudes right now, or these two quantities are unknown to us yet. We will discover them in a second, but the idea here is the following, that under the inversion of the parent plane, centered at the point O with the radius R large, the circle S1 must be taken into the circle S2, and under the same inversion, the circle S2 must be taken into the circle S1. In other words, the circles trade places under yet another inversion, so in some sense we have one level of indirection over here before we get to the inversion. So after, we need to go through another helper inversion, and the fact that these two circles must be taken one into the other with this inversion, symbolically, let's say we apply the same inversion to this, for example, for this relation one more time, in the same center with the same radius over here. Over here will be what? Another inversion with the same thing, but its image is S2. So this thing comes out to back to the circle S2. And now that we understand that if we can find a point O and the magnitude of the radius under which these two circles trade places, then pretty much the problem is solved. We're done, because once we construct that circle, we pick the point P anywhere on that circle. We pick the radius of that circle shown in blue, any real number for the length of the radius of that circle. We pick any real number strictly larger than 0, and then in that circle we reflect the given input circles, fixed, distinct, coplanar, not one located inside the other, with different radii. We reflect them into two circles that will be precisely equally sized. And now we just need to cover the technical details of how exactly do we find the radius R large and the center O of inversion with respect to which, or under which, the circles S1 and S2 are taken one into the other. And we recover the center and the radius of inversion under which the input circles S2 and S1 become the images of each other by using the idea that in this case the center of homotopy, or a center, in our case it's easier to work with the so-called external center of homotopy, doubles up as the center of inversion under which the corresponding two circles will be taken one into the other. And the way we show it is basically by observing that the points of interest on the two input circles are always located on the same side of a certain point that we will soon call the center of inversion, and that the product of distances from the proposed center of inversion to the corresponding points on these two input circles obey the algebraic formula that is the basic formula of inversive geometry when it comes to inversion of the real plane with respect to a circle. And we do it as follows in stages. It can be done in a number of different ways, but just to show that this is the case with the minimal amount of new material that we need, we will do it for specific points, such as the points C and D, then for the tangency points, and then we'll pick any point whatsoever. As such, we have the following possible legal juxtapositions of the input circles S2 and S1. The circles are not in contact and are strictly outside of each other. The circles are in contact and have precisely one point in common. They touch each other externally, and the two circles intersect. And in this case, in all these cases, we can construct both external and internal centers of homothenity. The basic idea for construction of the centers of homothenity is to construct any two parallel radii of the circles, for example, this one and this one, then take these points, construct a straight line, and then intersect that straight line with the line of centers. This is the basic idea that will always serve you well, but for demonstration purposes, I show that in this case, the centers of homothenity, the external and the internal, are located at the intersections of the corresponding tangents, external tangents or internal tangents. Here, the coefficient of homothenity is always strictly positive. Here, it will be negative because we need to flip things around. Here is the same deal. We can construct parallel radii, snap a line through the 2 points where the radii intersect the corresponding circles, draw the straight line of centers, and so on. You understand the technology. It's not too complicated. And when the circles intersect, the same exactly deal. We can construct two external tangents, and the internal tangents in this case will not work, but the center of the internal homothenity is still locatable. Look at this. Radii, arbitrary radii, and then from this circle, the radii in the other direction, parallel to the first one. And then the line of centers and the points where the radii intersect the corresponding circle. Boom, we have our internal center of homothenity, but this is beside the point for us. For the technical solution of the problem 29, it is sufficient to only deal with the external center of homothenity shown over here. And now we will show that that center of homothenity that can be located by constructing two external tangents or one tangent and the straight line of centers. That's even less work. Doubles up as the center of inversion with positive power, which takes our input circles S2 and S1 into each other, and we do it as follows. Let's say we constructed this one tangent tau 1 through the center, through the point O. That tangent will intersect the straight line of centers at the point O. And then A is the point where the tangent tau 1 touches the circle S2. B is the point where the tangent tau 1 touches the circle S1. O1 is the center of the circle S1. O2 is the center of the circle S2. We connect the points of tangency with the corresponding centers. We have, by definition, right triangles. They share the one and the same interior angle at the vertex O. The corresponding triangles are similar by angle, 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 and similar triangles by Euclid's Elements, Book 6, Proposition 4. The lengths of the sides about equal angles are in the same proportion where the corresponding sides lie opposite equal angles. So we construct this proportion. Basically, the hypotenuses of these triangles, OO1 and OO2, relate to the radii constructed like this in the same way, which is basically saying that this here angle is one and the same in both cases, but without attracting any trigonometry. This is what we have. Cross divide this ratio over here, put the first hypotenuse in the denominator, have a ratio of 2 radii, R2 divided by R1. The rate, remember that our circles are fixed. That means that the radii are fixed. The ratio of two constant numbers is a constant, so we designate it as K. This is our coefficient of homothenity. So once we know the radii, which we do, we're told that these radii are distinct. we know the coefficient of homotheity, and we know how to divide numbers with Euclidean tools alone, with the compass and the straight edge. And now this relation over here implies that we have this relation for the hypotenuse 002 and this relation, sorry, this one for the hypotenuse 001. It's k times r1, k times r2. Why? Divide this by this, k's and k's cancel out, and we have our ratio. Voila. And now we construct the product of distances from O to C and from O to D, from O to C, and again from O to D, and you understand where this is going. We want to show that under the power of inversion that's positive, this point is taken into this, and this point is taken into this. We just have to, we claim that this is the center of inversion, of the corresponding inversion. We just have to recover the magnitude of the length of the radius of inversion, the uppercase R. See, we're looking for this guy, for the uppercase R. Well, look at this. The product of these distances is quite straightforward. It's another baby observation. The distance from the point O to the point C is composite. It's our hypotenuse 001 plus R1, and the distance from the point O to the point D is the same hypotenuse 002 minus R2. So we have a plus in the first case, plus we have a minus. Through our, see, with these relations, we take these things over here, k times R1 plus R1 times k times R2 minus R2, factor out k2, factor out R2 both times and R1 in the other parenthesis. We have k minus 1 times k plus 1 times k minus 1. This is the difference of squares, k squared minus 1 times the product. Now, all these magnitudes are constant. Constant, this is constant, the square constant, product, difference, everything is a constant real number. Boom. We claim that this is precisely the square of the radius of inversion with positive power, under which the circle, we can see already S1 is taken into S2, S2 is taken into S1. Now, because we did it for special points C and D, where some people will say, okay, what happens when the circles touch and the points C and D merge into one? Well, in this case, we have these points. This will be D, this will be C. And what will you have for this distance? Well, you will simply flip the signs. Over here it will be minus, over here it will be plus. So still, you will have plus 1 times minus 1. The product of radii will be the same, and you will have the difference of squares anyway. Game over. In this case, you still have the same deal. You can take these 2 points or these 2 points. Again, it doesn't matter. The claim is you will always arrive at this expression over here, and now we'll do the same experiment, but for the points A and B. And for the points of tangency A and B, we develop the same product by observing that in this case, to these points A and B that belongs to the common external tangent Tau1 of both input circles S1 and S2, we can apply one and the same theorem from the theory of circles, which says that the square of the tangent drawn through the point is equal to the corresponding product that is applicable to any, this is one of the key situations here, applicable to any secant of the corresponding circle. Well, in this case, we will take the secant that runs through the centers of the input circles S1, S2, and we're home free. So we have it for the square of the distance OA, we have the following product. The secant that goes all the way out, so that's the distance O2 plus R2, this distance, and the secant that is trapped between the outer portion of the circle, B, and the point O, this distance right here, and this distance will be given the hypotenuse minus R2. So we have plus R2 minus R2. This will be the square of the difference of squares, 002 and R2. But again, the distance 002 we express, remember how, k times R2. Then we factor out R2 squared, and we have our result. And in exactly the same way, for the point B, the tangency point between the common external tangent Tau1 and the input circle S1, the same exactly deal. The square on that tangent is equal to the rectangle on what? OC or O01 plus R1 and up to here, O01 minus R1. So by the same reasoning, we have this relation over here. And once we construct the product of the distances from the center O to the point A and to the point B, we will have the following result. The distance OA times the distance OB is equal to the square root taken from the corresponding squares, which we just computed. And once we take the squares, we will have the same expression that we had in a few seconds ago in the previous segments. The length of the radius R1 times the length of the radius R2 times the square of the coefficient of homotheity minus 1. Again, all these numbers are constant, and not only that, that is precisely and exactly the same constant that we obtained in the previous segment. So this particular relation holds for the points A and B. They are also somewhat special because they are the tangency points, but they show that under the proposed inversion of the parent plane with positive power, because the points A and B, C and D here, or this point and this point are located on the same side of the center of inversion. Under that inversion, the corresponding points are taken into them, as I explained, C into D, D into C, or this point into this point, this point into this point. Here, B is taken into A is taken into B. Now we just have to roll through a similar argument where we will pick any point on the circle S1 or S2. That is, if we draw an arbitrary straight line through the center or in such a way that that straight line intersects both of the input circles S1 and S2, then that straight line will intersect the given circles at 4 distinct points. Let us name these points X1, X, Y, and Y1. And the argument over here is the following. We know that the point X is the homothetical image of the point Y1, or Y1 is the point X that is taken by the homothety centered at the point O with the coefficient K. Right here, X is taken into Y1 if the parent plane uniformly expanded. Again, let's say for demonstration purposes, it doesn't have to be that way, but we know that one circle must be smaller than the other. We name the smaller circle S1, the larger circle S2, it doesn't really matter. And let's say we execute the homothety centered at the point O of the parent plane with the coefficient that we already defined. You remember R2 divided by R1, and we agreed that R2 is strictly larger than R1. That means that the uniform expansion of the parent plane will eventually take the circle S1 into the circle S2. The point B will crawl into the point A. The point X will be taken into the point Y1, and the point X1 will be taken into the point Y. In other words, Y1 is the homothetical image of X, and Y is the homothetical image of X1. So here we're captured that fact by saying that the distance OX times the coefficient of homothety is equal to precisely the distance OY1. In some sense, this is the essence of this geometric transformation, to which we refer as the homothety of the parent plane centered at the point O with the coefficient K. Likewise, the point X1 is taken into the point Y. One more time, X1 is expanded all the way into the point Y. Again, by the homothety centered at the point O with the coefficient K. That means that the distance OX1 times K, which is greater than 1, is equal to the distance from the center of homothety to the point Y. That much we know. And then using these relations, this relation and this relation, we simply construct again the product OX, the distance from the point O to the point X, times the distance from the point O to the point Y. So the distance OX times the distance OY. Again, you see here we drive towards the idea that these 2 points are the inverse images of each other, but this time we pick these points at random. It doesn't really matter whatsoever. So OX is taken, the distance OX is taken from here. It's the distance OY1 divided by K, OY1 divided by K times the distance OY taken directly from here. We take it like this. So the coefficient of homotheity cancels out. So we have our product OY1 times OX1. But look at this, at the same time, our straight line that passes through the center O, shown in green, this arbitrary straight line, is what is a second. It generates actually 2 seconds of both circles of the circle S2, circle S1. So by the corresponding theorem, we take it the square of the tangent divided by the smaller segment of the second from the point Y to the point O. Because remember, this is the power of the theorem from the corresponding theory of circles, that the square on the tangent is equal to the rectangle on any, as Euclid puts it, rectangle on any second. The second OY1 is one such second, so we have this relation over here. And for the second OX1, look at this, OX1 will be equal to the square on the tangent OB divided by OX, the distance OX. And once we put these relations, this relation and this relation over here, we will have our product of squares divided by this product. But look, this product again sits over here, so we have the distance OX squared times the distance OY squared is the product of the squares of our what? Of our tangents. And for these tangents, we already showed in the previous segment that this relation holds. And there you go. This is exactly what we were driving at. This shows that we can write it down for any point X on the circle S1 and for any point Y on the circle S2 by our definition of the power of inversion. The points X and Y are located on the same side of the center of inversion. They honor this relation over here. This is a constant for everything fixed on the input side. This is precisely one and the same number. Regardless, it does not depend on the choice of the points X and Y. This is a constant. This is R squared. So consequently, we know that the mystery radius of inversion will be square root of R1 times R2 times K squared minus 1. We take this square root like this, so we now know the magnitude or the length of the radius of inversion. We know how to locate the point O. We have a plethora of methods. We can construct any two radii that are parallel, take these points, run the line through, and when this line intersects the straight line of centers, boom, we have our point. Doesn't really matter. We can construct the straight line of centers, snap one common tangent. Also, it will be in the same point O. We know how to locate the point O. We know how to construct. This is all constructible. All these operations over here can be carried out with Euclidean tools alone, with a straight edge, with incredible simulation and a compass. We know how to multiply, divide. We know how to extract the square root. This problem is all solvable. And now, of course, my drawing by eye and by hand is somewhat imprecise, somewhat goofy a little bit, but if all the ideas that we discussed in the previous segments is captured professionally in the graphing software, in my case, GeoGebra, the free software called GeoGebra, then it will look as follows. Now that we understand how the problem number 29 can be solved, we clean up our mess and wrap it up into a nice package that we call an algorithm that solves the given problem. That is, our algorithm for solving the problem 29 is as follows. As a step number 1, we want to find a point O such that under the inversion of the parent plane with positive power, centered at the point O with the radius R that is shown over here, the magnitude of the radius of inversion is equal to the square root of the product, the length of the radius of the input circle R1, the length of the radius of the input circle to R2 times the difference of squares as follows: K squared minus 1. Under that inversion, the circles S1 and S2 will be the images of each other. In other words, that inversion will take the circle S1 into the circle S2, and conversely, it will take the circle S2 into the circle S1. Now construct the circle that is centered at the point O and has the radius r specified over here. Next, pick any point P on that circle L. We refer to that circle as L. Pick any point P on the circle L and make the radius of inversion any strictly positive real number whatsoever. And as the final step, simply reflect the given circles S1, 2 in that circle centered at the point P with the radius r into the circles S prime 1, 2, and it will so happen that the radii of the reflected circles will be precisely and identically equal to one another. Of course, no presentation or no discussion of inversive geometry without some form of animation or a visual demonstration is complete. That is why I prepared the following animation for you. And the idea here is the following. I'm not going into all these pedantic details of how degrees of freedom does this problem have. Well, at least we know that there are 2 degrees of freedom, which are captured which way. Remember, 1 degree of freedom is given by this clause over here. Any point P on our circle L, that's 1 degree of freedom, or the freedom of the point P to roam the periphery of the circle L, with respect to which our input circles are taken one inside the other. And the 2nd degree of freedom is we take any real number r greater than 0. So the radius of inversion or the actual length of the radius of inversion is also irrelevant. Any legal positive real strictly positive real number will do. So exercising these 2 degrees of freedom, the freedom of the point P run over the circle L, and making sure that the radius of the inversion over here R is picked at random, I've put together a demonstration for you using the free software called GeoGebra. But wait, there is more. The magic of inversive geometry has another present for us in the store. Recalling our discussion of degrees of freedom in this problem a few seconds ago, we know that the radius of inversion r for the circle of inversion that will produce the pair of circles of equal size is irrelevant. And what does that mean? That means that we can very well make the circle of inversion C orthogonal either to the input circle S1 or to the input circle S2. And in that case, what will happen? Well, we know if 2 circles are orthogonal, then in this case, the circle S1 will be invariant with respect to the inversion in that circle, and it will be taken into itself. S1 will be taken into itself, but the circle S2 will be taken into a circle S prime 2, and the radius of that circle S prime 2 will be exactly what? It will be exactly the radius of the circle R1, if we wish to do so. This is just a fun exercise simply because we can. A little intellectual exercise. And if we make the circle of inversion C orthogonal to the circle S2, then the circle S2 under that inversion will be taken into itself, but the circle S1 will be taken into a circle S prime 1, such that the radius of the reflected circle S prime 1 will be equal precisely to the radius of the input circle R2. And this is also a fun exercise. We can make it so happen if we construct the circle of inversion C so as to be orthogonal to one of the input circles. And how can we do that? Well, look at this. If we have our point P, all we have to do is construct any one tangent to the target circle S, S1 or S2, from that point to that circle. That means that the radius from constructed from the center of that circle to the point of tangency will be perpendicular to that tangent. And through that point over here, we construct precisely our circle of inversion C. And the circle of inversion C will be exactly orthogonal to that circle. And this is it. That task can be carried out with Euclidean tools alone. Now, this is it for the problem number 29. This is it for all the tactical adventures in this course. And I will see you in the next episode, the episode number 29, which will be the final episode of this course altogether. And in that episode, I will give you several directions in which you can deepen your knowledge of inversive geometry.